Hello, this is IC Engine Systems Lab with me, Riley, Colin, Miggy, and Tyler. So to introduce what we're doing, so the background, Generative Energy Systems Incorporated, they've developed a modular internal combustion engine. Our objective as Burdell Incorporated is to determine the system parameters and control for that specific engine. So the overall plan is over the course of several experiments, over a course of a couple weeks, we're going to do different engine setups that have different assumptions. And from those assumptions, we can build a comprehensive model of the internal combustion engine. Once we have this comprehensive model, we can maximize the work output of the engine. Like I said, over the course of 3 weeks, we will conduct various tests to characterize mechanical and fluid properties of the system. So looking at the weekly plan, week 1, we're going to perform a kinetic energy analysis, which we're going to be performing a work kinetic energy analysis on all 3 weeks. On week 1, the analysis will be on an engine subsystem without the head and with no pressure. So from that, we'll be able to obtain a model of the flywheel inertia and all the friction effects. On week 2, we're going to perform another energy analysis with this subsystem, though, with the head on without any injected pressure. This means there's going to be air within the system. We're not going to be adding any more, but that air will have some pressure effects. So from there, we can obtain model parameters of those pressurization effects. On week 3, we're going to do an energy analysis on the entire system in full operation. This means head on, and we're going to be adding additional pressure to simulate combustion. From there, we can obtain full model parameters describing the entire engine, including combustion. So on week 1, we're going to assume that the work from the piston is negligible and the coefficient of friction is constant. We actually made both of those assumptions for all 3 weeks, as you can see. Also in week 1, we're going to assume that work from air is negligible. That is because the engine head is off. On week 2, along with work from the piston and coefficient of friction assumptions, we're assuming that work from air in the power stroke is equal to the opposite work in the air in compression stroke. So they're equal but opposite forces there. We're also going to assume that atmospheric pressure is 104,351 pascals. On week 3, similar, like I said, we already made the work from the piston assumptions, coefficient friction assumptions, and the atmospheric pressure assumptions. We're also going to assume that the pressure at air injection start is equal to the pressure at air injection cutoff. So when we inject air, the pressure at its start and the pressure at its end is going to be the same, which is going to be around 620,500 pascals, also known as pressure line absolute. So for our methods, you can see the system here. We have the internal combustion engine, the motor on the left, and the pneumatics. So the system is composed of that internal combustion engine, torque sensors, which are attached to the motor, removable flywheels, which are the 4 discs you can see on the right, and an encoder, and that will determine how fast the motor is spinning.
Okay, so before beginning data collection, it was important to calibrate the force transducer to define the relationship between voltage and torque on the system. This was done weekly by taking data points as known masses were added to a moment arm attached to the system. This allowed us to observe a voltage reading resulting directly from the torque applied, and looking at the graph on the right here, you can see that a calibration equation was derived both for the process of increasing torque as well as decreasing torque. The final calibration equation we used was an average of these 2 equations. And moving on to the work energy balance, we begin to start thinking about how we can characterize the engine as a whole. So it was useful to define the work energy balance of the system as seen right here. And aside from what could be directly measured, the unknowns of the system are frictional work, piston work, work done by air, flywheel inertia, and an error work term that accounts for the discrepancy between the model and our experimental setup. These are terms that we need to derive experimentally. Here you can see the roadmap to accomplishing just that. While we will get more in depth on these processes later on in the presentation, it is important to note that deriving these terms required physical changes to our experimental setup to isolate the desired work terms. An immediate example of this is the procedure for week 1, where experimentation was done with the engine head removed to eliminate the work done by air term. Other assumptions made include that the work done by the piston could be ignored since frictional work should be much greater in comparison with a large enough flywheel inertia. After collecting data, the frictional work was calculated by numerical integration over the steady state portion of our data, as seen on the graph on the right. To calculate the flywheel inertia term, the work energy balance was solved using the calculated motor and frictional work terms. The theoretical value for flywheel inertia was also calculated to serve as a comparison tool. And now with the values for both work terms and the flywheel inertia, the work energy balance for the headless engine is now fully defined. It can be seen here that the frictional torque values followed the Coulomb friction model, as there was a slight increase due to RPM, but this was not significant enough to represent a Newtonian model. There was, however, significant error associated with our calculated flywheel inertia values compared to the theoretical value by around 66%. The team thinks that this could be due in part to the wobble present in the system.
Moving into week 2, we'll be calculating the work done by air. So we'll have the engine head on, but still no air injection. Adding the engine head adds in the work term to the work energy balance equation shown earlier. So from week 1, we had made the assumption that work from the piston was 0. We had solved for frictional work using the frictional torque, and we'd also solved for the flywheel inertia. We are also still assuming that the discrepancy term is equal to 0. Moving into week 2, we have measured the work from the motor and the angular velocities of the flywheel, and the only unknown in this equation is work from air. So for this set of experiments, we'll be analyzing each stroke of the engine stroke model from intake to compression to power to exhaust. So during intake and exhaust, the valves are open and there's negligible work. However, and the work from air is equal to 0. But because we're trying to solve for work from the air, we'll be focusing on compression and power. During compression, we have adiabatic compression. During the power stroke, we have 2 major cases. 1, when there's no injection of air, adiabatic expansion, and 2, when air is injected. This is constant pressure expansion. We'll be focusing on case 1. So here's just a review of the equations that apply during each stroke. As mentioned before, we'll be focusing on compression and power, and we'll be solving for work from air using the equation shown earlier. So because we'll be looking at each stroke, we'll be analyzing the encoder data to find where each stroke is happening. So to do this, we'll be looking at the angular position. Because there are 2 revolutions per engine cycle, we'll be looking at a range of 0 to 720 degrees. Every 180 degrees, we'll be going through a different stroke. And as you can see here, there's a clear peak in torque between compression and power. This is for the 0 flywheels, low speed case. However, increasing the number of flywheels, as shown here, adds in some noise in the data, and there's no longer a clear trend. In comparison to 0 flywheels and low RPM, you can see that the engine is going through 3 cycles. And a similar effect can be seen with increasing the RPM, even with 0 flywheels. Having a high RPM increases the noise, and there's no longer a clear trend in data. So through our analysis, we saw that the medium and low speed for 0 flywheels had the clearest data, but the rest of it had a lot of noise.
Here are the final results from week 2 of the work done by air values. Theoretically, the work done by air in the compression stroke should equal negative the value of the work done by air in the power stroke. This was determined to be about 20 joules, and this should be a constant value across speeds because the calculation of this value only depends on other constant values. There's a very significant difference between the theoretical value and the value we calculated experimentally, and this experimental value is about an order of magnitude higher than theoretical. We believe this is due to faulty data. There's a lot of noise in the data collected from these experiments, and this could have contributed to the discrepancy. Here are the uncertainties that we found overall with the work. The 2 main ones that we found in the beginning were from the Elvis and the calibration mass combined uncertainty. And with these 2, we were able to find the combined uncertainty of the torque and the angular displacement per encoder bin. And then finally, the final uncertainty of the cumulative work done by the motor on the flywheel was found to be 3.172 joules. The next steps for the team are to calculate the discrepancy term, which is found between the experimental and model value for the work done by the air. And in week 3, we're going to be able to determine this because they'll have the simulated combustion by injecting the air, so there will actually be more work done in the power stroke than there was in week 2, and we will be able to determine this discrepancy term. The final deliverables to the client will be a model of the IC engine, the whole work energy balance and its validity, also an optimal angle range for which air injection should occur to maximize work. And also we are going to examine the discrepancy term and whether the provided sensors are viable for detecting whether this term exceeds the uncertainty. And finally, an estimate of the maximum work output of the engine occurring at full braking load. Here are our citations. Thank you so much.